Hey everyone, and welcome. Today we're going to roll up our sleeves and really sink our teeth into a classic kinematics problem, one from a truly legendary physics textbook. Trust me, it's a fantastic challenge that's really going to test how well you understand motion. So let's just dive right in. So if you've ever studied physics or engineering, you've probably heard the name Irodov. His book, Problems in General Physics, is, well, it's famous, or maybe infamous, for its incredibly challenging problems. They're the kind that really force you to understand the fundamentals. And today, we're going to decode one of them together. The problem we're taking on is number 1.42, right from the kinematics section. And it's a real gem. It looks pretty simple on the surface, but it's designed to make us be super precise about the physics of moving along a curved path. Okay, let's unpack this. We've got a particle, it's moving along some path y of x, and here's the key detail. Its velocity v has a constant modulus. That's just a fancy way of saying its speed isn't changing. So our job is to find two things, the particle's acceleration and the path's radius of curvature, but only at the specific point where x equals 0. And we have to do it for two different paths, first a parabola and then an ellipse. Right away, this is a classic trap. You hear constant speed and your brain might just scream 0 acceleration, right? But hold on. Remember, velocity is a vector. It's got speed, sure, but it also has a direction. If you're moving on a curve, your direction is always changing, even if your speedometer is stuck at 60. And any change in velocity, whether it's speed or direction, means you absolutely have an acceleration. So before we start crunching any numbers, we gotta make sure our toolkit is ready. Honestly, understanding the core concepts here is what turns a problem that seems impossible into something totally manageable. The kind of acceleration we're talking about here is called normal acceleration. You might know it by another name, centripetal acceleration. Its one and only job is to change the particle's direction. It's always pulling perpendicular to the way the particle is going, tugging it toward the inside of the curve. It's what forces the particle to turn without actually making it go any faster or slower. And these two equations, these are the keys to the whole kingdom. First, the normal acceleration is just the speed, v, squared divided by r. Simple enough. So what's r? That's the radius of curvature. Just think of it like this. It's the radius of a circle that would perfectly hug the curve at that one specific spot. A really sharp turn has a tiny r, a long sweeping turn has a huge r. And to find it, we use this beast of a formula from calculus. It looks intimidating, I know, but it really just depends on the path's first and second derivatives, what we'll call y prime and y double prime. Okay, we've got our tools, we understand the concepts. Let's get to work. First up, the particle moving on a parabola. The equation for our first path is nice and simple, y equals a times x squared. A is just some constant that tells us how steep the parabola is. So here's our game plan, step by step. First, we'll find the first derivative, y prime. That just gives us the slope of the path. Then we get the second derivative, y double prime, which tells us how that slope is changing. In other words, it's a measure of the curve itself. We'll find the values of both right at our point of interest, x equals 0, and then we plug them into that big formula for r. Once we have r, getting the acceleration is the easy part. All right, let's do it. The first derivative of ax squared, that's just 2ax. At x equals 0, that's, well, it's 0. Super simple. The second derivative is even easier. It's just the constant 2a. Now we plug those into our radius formula. Because y prime is 0, that whole top part of the formula simplifies like crazy, and we're left with this beautiful, clean result. R equals 1 over 2a. And now for the final piece of the puzzle. The acceleration is v squared divided by r. So we take v squared divided by our result of 1 over 2a, and that flips around to give us 2a times v squared. And think about the direction for a second. At x equals 0, we're at the very bottom, the vertex of the parabola. The path is perfectly flat for an instant. That means the acceleration, that pull, has to be pointing straight up, purely in the positive y direction. Perfect. One down. Now, let's take the exact same method and apply it to the second case, the ellipse. The physics is completely identical, but the calculus is going to be a little more spicy. So here's our standard equation for an ellipse. You'll notice that y isn't written out nicely as a function of x. That just means we get to use a really cool technique called implicit differentiation to find our derivatives. Our strategy? It is exactly the same. Don't let the different equation fool you. We'll differentiate to get y prime, do it again to get y double prime. We'll evaluate both at x equals 0, pop them into the radius formula, and then use that result to get our acceleration. See, the physics hasn't changed one bit. So after we work through the implicit differentiation to find y prime and y double prime, and it does involve a bit of algebra, not gonna lie, we can then evaluate them at x equals 0. That point corresponds to either the very top or the very bottom of the ellipse. And just like before, everything simplifies down beautifully, and the radius of curvature comes out to be a squared divided by b. And finally, the acceleration. We just take v squared and divide by our new r. So the acceleration at the top or bottom of this ellipse is v squared times b, all divided by a squared. This just shows so clearly how the acceleration depends entirely on the geometry of the ellipse itself, its two axes, a and b. Excellent work. We've crunched all the numbers, we've got our answers. Now it's time to zoom out for a second and really synthesize what we've figured out from tackling this problem. Check this out. Here are our results side by side. Look how the exact same physical principle, that acceleration is v squared over r, gives two totally different looking answers. It all comes down to the geometry. The acceleration you need to keep a particle on a path is dictated entirely by how sharply that path is bending at that exact moment in time. So what are the big takeaways here? First, and this is the most important one, acceleration is about any change in velocity, not just a change in speed. Second, for anything moving on a curve, that change is driven by normal acceleration, which is always v squared over r. Third, that r, the radius of curvature, is the crucial link connecting the geometry of the path to the physics of the motion. And finally, you now have a powerful, repeatable method you can use to analyze motion on pretty much any curve you can write an equation for. We solved this for one specific point, x equals 0. But here's a final thought I want to leave you with. Using this exact same method, what do you think would happen at other points on the ellipse? Like, say, at the widest parts on the sides? Where would the curve be the sharpest, meaning r is the smallest, and where would it be the flattest, with the largest r? Working that out for yourself is going to give you a much deeper feel for this beautiful connection between geometry and motion. Thanks for watching.